Please don't forget to add your homework to the pile. Also, if anybody didn't pick up their exam last time or homework last time, let's see, Mr. Oakley and Richardson. So this is just homework from last time. Anyway, well, good morning, everybody. So again, don't forget to turn your homework in today. I'll post the solutions in the case outside my office, as I do every Wednesday after class. So today we're just going to continue with this discussion of thermodynamic property relations. The first thing I want to do is just remind you that this is Cal Poly. While we certainly want to make sure you have an appropriate let's say, technical understanding, theoretical understanding of the thermodynamics, the emphasis here has always been on, hands-on, more realistic problems. I'm certainly not going to emphasize the thermodynamic property relations in this class. In fact, we're only going to spend this 1 week on the material. If this were Caltech or UCLA or something like that, then very likely I would spend a month dealing with this, and also expect that half of you are going to go into research or academia, and you would need this kind of background. Here, most of us are just going to become engineers. We're not going to necessarily go on to do research or go into academia. So I just simply don't emphasize this material in this particular course. It is still important. We certainly all need to understand that somehow somebody has to generate the thermodynamic property tables that we use on a daily basis, and the various equations that we're talking about are the way that we do generate these tables. Now, last time I derived some basic relationships, which are called the Maxwell relations. Following that, I went through just one analysis that I called the bounding analysis that allows you to essentially verify that the Maxwell relation works, that is a valid relationship. If one were to have solved that example problem out in the real world, not as an example, but a real world problem, well, then you're not going to have thermodynamic property tables. You would actually be taking data, right? Temperature data, pressure data, volume data, mass data, and then using those various differential relationships generate the unknowns. In fact, the Maxwell relations are all relations between entropy, you've probably noticed this, entropy, and the other measurable properties, pressure, temperature, and volume, right? So if one were to try to put together tables of entropy, you would need to go into a lab and find the data, the measurable data, so that you can then use these equations to generate the non-measurable data. Now, this is what we're going to be talking about this week. So bear with it. If you're not that technologically savvy, if partial differential calculus was never your thing, that's okay. We'll get through this. And again, just be comfortable knowing that this is not going to be a main emphasis in this particular class. Nonetheless, there's a certain elegance to mathematical relationships, going through certain proofs and all that. Certainly we do find something interesting in that, even if perhaps we're not going to use this material on a daily basis. So with all this having been said, let's move on to another equation that has to be derived called the Clapeyron equation. Okay, so the Clapeyron equation is actually an equation that's used to find information in the saturation region. So this equation specifically applies to the saturation region. Okay. In other words, where we have a phase change, we're looking at the phase change between a liquid and a vapor typically. So what we want to do is actually derive this Clapeyron equation, again noting that it's something that we're going to deal with in the saturation region. And we're actually going to begin this particular derivation with the third Maxwell relation. So just recall last time as I derived the Maxwell relations, I numbered them M1, M2, M3, M4. So M3 is simply the third Maxwell relation. And it's this one, the partial of S with respect to V holding T constant equals a partial of P with respect to T holding V constant. Okay, so this is the relationship that we're talking about. Right. So what do we do with it? So let's just consider an isothermal phase change. And this isothermal phase change will go through the entire saturation region. So in other words, from a saturated liquid to a saturated vapor. Okay, so what we want to do first is note that in the saturation region, pressure and temperature are not independent properties. This is something we know. If the phase change is taking place, then at any one particular temperature, there's only one possible pressure, or vice versa. So pressure is only a function of temperature. Okay, so again, this is something that I want to note, but I think it's something that we already understand. Now, since pressure is only a function of temperature, then look at what we have here on the right side of this third Maxwell relation. I mean, that's a partial of P with respect to T holding V constant. But P is only a function of temperature. It's not a function of volume at all. So therefore, we can actually rewrite that. And instead of saying that it's the partial of P with respect to T holding V constant, it's actually just going to be dP dt. Now, granted, this only applies in the saturation region, right? So often what we do in this particular case, just as a reminder, is just put the little word sat down there, just to remind us that we're talking about this process in saturation region only. So therefore, if we go back to the third Maxwell relation, I'm just going to rewrite it. So it'll be del S, del V, T. And that just equals dP dt in the saturation region. Okay. Now, we might also note that this can be approximated. So we can approximate this as follows. So what I want to do is actually look at the left-hand side of the equation. At any constant temperature, I mean, we are just looking at the isothermal phase change, right? So isothermal, of course, meaning constant temperature. Well, if it's a constant temperature process, then we could just write this instead of del S, del V. Well, we'll just note this is S at the end of the phase change minus S at the beginning. So we'll just write this as SG minus SF. And then in the denominator, the change in specific volume is just Vg minus Vf. Okay, so this then equals dP dt in the saturation region. And in fact, we can even simplify this. We know that Sg minus Sf is what we just call SFG, and Vg minus Vf is just VFG. So let's just rewrite this. And we get SFG over VFG equals dP dt in the saturation region. Okay. Now, the next thing I want to do is just keep this equation in mind. We'll come back to it shortly. But now, let's use equation 2. Now, keep in mind that equation 2 was the second of the TDS relationships that was first presented to you back in Chapter 7, and now we're in, Chapter 12 or something like that. So I call it equation 2. This is in your notes from last time. And basically, that's just the equation that TDS equals dH minus VdP. Okay. Now let's keep in mind that this is an isothermal phase change, right? If there's no change in temperature, there's also no change in pressure. So this dP term has to go away, right? No change in pressure, dP is equal to 0. So therefore, TdS is simply equal to dH. Now, if we integrate in the saturation region again, and again, this would just be from saturated liquid to saturated vapor, we would basically show this as T times Sg minus Sf, and then this will equal Hg minus Hf. And then this too can be rewritten. We know that Sg minus Sf is just Sfg, and Hg minus Hf is Hfg. So basically we have now that Sfg equals Hfg over the temperature. And now what we can do is we can plug this back in to the equation above, right? So plug in above. In order to get the following. So instead of Sfg, of course, we have Hfg over T. Then we have our VFG. And then this equals dP dt in the saturation region. Okay? And this is the Clapeyron equation. So usually we reverse the order. We show this as dP dt in the saturation region is just Hfg over T times VFG. And this is the actual Clapeyron equation. Okay. Yes?
Once again, why could we say that the VDP was equal to 0?
It's actually the dP part of the VDP that's equal to 0, and it's just because of the fact that we're talking about an isothermal phase change and that P is a function of temperature only. So if there's no change in temperature, there can't be a change in pressure. I mean, that's just the nature of the saturation region. So dP is 0 for this particular example, and that's just what leaves us with this equation. Anyway, any other questions on this? Okay. Now, if you think about it, this is exactly the kind of equation that we're looking for. In our research world, we're trying to find equations that relate the measurable properties, pressure, temperature, volume, to the not measurable properties, like enthalpy. So this would allow us to go into a lab, take very precise data, and figure out what the enthalpy of vaporization is, what the HFG term is for a particular phase change process. So this is a Clapeyron equation. Let me give you one more example. Well, maybe I should say, let me give you one example. And this will use the Clapeyron equation. Essentially what I'd like to do here is find HFG for water at 300 kilopascals. Okay. And maybe I should say using bounding analysis, because quite frankly, we could just look this data up in a table if we wanted to. But that's not the intention here, right? It's to pretend that the tables don't exist and that the data in the tables is really just research data. So let's find HFG for water at this pressure using the bounding analysis. And again, this is the same method that we used last time. And why don't we also compare to the data in our tables. And of course, this is for water. So we're talking about table A6, right? All right, so how do we do this problem? Well, we're trying to find HFG. So we start with the Clapeyron equation. In fact, I'm going to rewrite this in terms of HFG. So HFG is just going to equal temperature times VFG, and then times dP dt in the saturation region. Okay. Now, remember with this bounding analysis, we're actually using some approximations. So we can approximate this as follows. So HFG is what we're trying to find, so we'll leave that in place. The temperature is simply going to be, well, the saturation temperature that corresponds to this pressure. That's something easily measurable. So that temperature is just Tsat at the given pressure of 300 kilopascals. VFG could just simply be written as the difference between VG and VF. And again, this is going to be at that same pressure, 300 kilopascals. Okay. And then dP dt, well, here's where we're going to have to actually do our bound. Here we could just write this as delta P over delta T, and then go into our tables and just look at the data and see what data bounds this pressure of 300 kilopascals. In fact, what you'll find is that in these tables, there's going to be another table at 275 kilopascals. That'll be one subtable over, if you will, from 300. And then there's another subtable to the right, which is at 325 kilopascals. So that's where we're going to take our bounding data. Again, it's as if we were in the lab recording all this data ourselves. So HFG then is Tsat at 300 kilopascals. Again, VG minus VF at 300 kilopascals. And then as we do our bounding, this would be 325 minus 275 kilopascals. Okay. And then when you go into these tables, there's going to be a certain saturation temperature at 325 kilopascals minus the saturation temperature at 275 kilopascals. And as I'm saying all this, I realize I've made a little mistake in my wording. This is all in the saturation region, so I don't know why I'm thinking table A6. Table A5 is our pressure table that corresponds to the saturation region. So this needs to say A5. Okay, and then I mentioned the subtables in table A6. That's not applicable here. We're just looking at table A5. It lists our data in increasing order of pressure. So we've got data at 325. We've got data at 275. We've got those as the bound around 300. So that's what really should be said here. All right, so this now is the equation we have to solve. So just go into our tables, look up the data. We find that the saturation temperature is 133.52. But we would note that whenever we're using temperature within an equation, we actually use one of the absolute temperature scales. So I better add 273.15 onto that to turn it into Kelvin. We would then look up VG and VF at 300 kilopascals. So this is 0.60528, and then minus 0.001073. And these units are both going to be meters cubed per kilogram. And then we have our pressure difference. Obviously, that's 50 kilopascal. And then the saturation temperature at 325 is 136.27 degrees C. And at 275, it's 130.58 degrees C. Now, this is a temperature difference, right? And we know that a unit of degree in Celsius is exactly the same as in Kelvin. So the temperature difference in Celsius is actually the same as in Kelvin. So I don't actually have to add 273.15. I can add it to each term, and then they'd cancel out anyway. But nonetheless, we understand that this is in Kelvin. So 1 degree of Celsius is equal to Kelvin at this point. So again, just keep that in mind. All right, so it's really just a matter of going through the mathematics now, and in doing so, we get 2161.1. Now, the units are going to appear odd. I mean, this is enthalpy, really specific enthalpy, so it should be kilojoules per kilogram, but I don't see any kilojoules up there anywhere. But we've done this before. We know that a kilopascal is a kilonewton per square meter. We know that a kilojoule is a kilonewton meter. And now you can see that everything's just going to cancel out, and the only units that remain are kilojoules per kilogram. So kilojoules per kilogram And this would be the solution to this problem using our bounding analysis on the Clapeyron equation. Now, we compare this to what's in the table. If we go into table A5 at 300 kilopascal, we would find that HFG is a little bit different. It's actually 2163.5 kilojoules per kilogram. So you might want to look at those two numbers and consider whether we've done it right. But the fact is, we're only off by what, 2.4 parts out of 2,000? So that's what, about 0.1%? So that's a very, very small error, especially when you consider that our bounding analysis was done over a very wide range of pressures and temperatures, right? If we were doing this in a lab, our bounds would be quite a bit tighter. You know, we'd have data at 300 kilopascals, at 300.5 kilopascals, at 299.5 kilopascals. Our bound would be much tighter, and the error introduced would then be a lot less, and we probably would end up with something that's quite a bit closer to this number. So, nonetheless, I would conclude that these numbers are the same and that we've validated this particular Clapeyron equation at this particular pressure. So there is a problem that deals with thermodynamic property relations in the Clapeyron equation. So any questions on this? Yeah.
So is this to verify what like the specific entropy at that point is, or is it to find what the specific entropy is?
Well, both, depending upon your situation, right? I mean, if you're in a lab, then it's to find this value. I mean, some researcher found that value, and that's why it's in the table. But of course, in this class, we're looking at it differently. We're assuming that we're just using the data that's in our tables, and we're just validating information that already exists. But again, think about it as if you're a researcher somewhere, and that the tables are really just the data you've taken in a lab, and that the equations are what you're solving to find additional information that's going to then go into the future thermodynamic property tables. And by the way, this research goes on all the time. Thermodynamic property tables are continually being reviewed. There's international conferences every number of years where researchers from all over the world come together, compare their notes and data, generate new updated property tables, and that just continues. Every year it happens. Yes?
So we're only going to use this for water in R134A class?
Well, yeah. Although, you know, I've been known to find property data for other substances and maybe other thermodynamics textbooks, but as long as you understand how to do this type of problem, it doesn't really matter what substance I give you. But yeah, in general, right, only water and R134A. That's the only data we have, and that's likely going to be the only problems we'll ever see. Yeah. Okay. Well, let's find some other relationships. Now, again, we understand that we're trying to find relationships for properties that are not measurable. So what could we do? What else could we do that we haven't yet done? Well, let's go back to the general statement. So let's find more relations between the measurable and the unmeasurable. Okay. These are actually the properties that we're going to use almost exclusively, right? We've gone through a full course and a half now in thermodynamics. We've never really used any other properties beyond these, right? So this is what we're going to do in this class. We're going to try to find other relationships that will allow us to generate the data for specific enthalpy, entropy, enthalpy, internal energy, entropy, and the two specific heats. So that's what we're really looking for. So let's do this. Let's say that we want to look at internal energy as a function of temperature and specific volume. And if we have a property, an intensive property like U, in terms of two other independent intensive properties like temperature and specific volume, then this could be written in the form of the equation A, which I presented last time. So from this equation, we write in the form of A the following. Now, remember, A was this equation where you're able to take one property and turn it into a relationship between partial differentials of those properties. So du is equal to del u del t v dt, and then plus del u del vt dv. Okay, so this was the form that I've called equation A. And again, this is in your notes from last time, so you should have this already somewhere. This particular equation I'm going to call equation 5. So I'm going to just keep numbering these equations continuously from last time. This can be confusing enough if I start renumbering equations starting at 1 or A every day. Many of you are just going to get lost. I expect half of you are going to get lost anyway, but hopefully that won't happen. We'll see. If you're already lost, I don't know, hopefully you have a nice game on your phone. I shouldn't say that. Pay a little more attention, and hopefully I'll make it fun and interesting. But nonetheless, we start at this particular equation, and then what I want to do is let's just take its partial with respect to v holding t constant. Actually, I want to take the partial with respect to v holding t constant, not of this particular equation, but of the equation 1, which was the first of our TDS relations. Okay, so this equation 1 is du equals TDS minus PdV. This is equation 1. So we rewrite it in this form. So we have del u del v t. And this is going to equal t, and then del s del v t minus, now please note here we're taking the partial with respect to v of dv, so that's just going to be 1, so minus p. Well, minus p times 1, the dv of course is just equal to 1. Okay. And now what I want to do is I want to plug the third Maxwell relation into the above. Okay. And the third Maxwell relation is the one that relates del S del Vt. So I'm going to plug that into the equation above. And we'll get the following. So we get del U del Vt equals, and then here making the substitution, the third Maxwell relation I haven't written down, but it basically says that del S del Vt is equal to del P del Tv. So this equals, first of all, temperature, and then del P del Tv minus the pressure. All right, so that's our next step in this particular process. Now let's also note that we also want to note that the specific heat at constant volume is defined as the partial of U with respect to T holding V constant. Okay. And what I want to do then is I want to take both these equations and actually want to plug them all the way back into the equation that I called 5. I mean, after all, we have a del U del Vt term here, and we have a del U del Tv term, which is Cv. So I'm going to plug both those into 5 above in order to get the following. And we get du equals Cv dt plus T del P del Tv minus P dV. And by the way, I very likely will make at least 1 or 2, let's call them typos, as we're going through all this. I mean, I'm reading my notes, but I don't know, my notes are not real neat. I can hardly read my own notes sometimes. So if I don't have something quite right and you recognize it, just let me know so I can fix it. Nonetheless, this is the equation we have. In fact, I'm going to call this one equation 5a. And then the last thing I want to do is I just want to integrate. So du, of course, now is going to be the integral of du, which is just u2 minus u1. Then we have the integral, and we're integrating on temperature here, so between T1 and T2 of CV dt. Okay. And then here we're integrating on volume, so plus the integral from V1 to V2 of T, and then del P del TV minus P dV. All right, so here's another equation. So basically, these various equations that I'm underlining are what we're looking for. What are we trying to do again? We're trying to find relationships between measurable and not measurable properties. Now here, unfortunately, we have not only internal energy, but also CV. But nonetheless, there will be ways to deal with that, and we'll get to that later. But nonetheless, everything else is really in terms of what is measurable. So we should be able to utilize this in some way, again, to find relationships for U and CV in terms of the properties that are measurable. So here's another equation, another thermodynamic property relation that we find is going to be very useful. Again, very useful if you're a researcher. And now let's generate some more. So I don't think I'm going to go through the full derivation like I've just done, but this next derivation is very, very similar. So why don't I just write it this way? Similarly, so when I say similar, I'm really going all the way back to the first statement there, which says from. So similarly, and now let's look at a different relationship. Let's look at enthalpy as a function of temperature and pressure. And again, this will be written in the form of equation A. So we would have dH equals, and then here we would have del H del PT dt, and then plus del H del T P dP. Okay. And this equation I'm going to call equation 6. Okay. So we've done the same thing here for enthalpy in terms of these two properties that we did over here for internal energy in terms of those two properties. It's the same procedure. And now I want to do more or less the same thing. So again, I'm not going to go through every single step here, but the next step is going to be that I want to take the partial with respect to P holding T constant of the second TDS relationship, the one that's called 2. So this is the one that's dH is going to equal TDS plus PdV. Right? This was the second TDS relationship. Okay. So if we take this and then, like we've done over here, I mean, I'm going to skip this step, but then I'm going to plug the fourth Maxwell relation into that. So after I've taken the partial with respect to P holding T constant of equation 2, I then plug in the fourth Maxwell relation. We also use the fact that Cp, kind of like we've done here for Cv, but now we're going to do it for Cp. So again, we take del PT of 2. We then plug in the fourth Maxwell relation. We use our definition of specific heat at constant pressure. So that's del H del T P. And then plug into equation 6. Now, certainly anybody who wants to can go through the same derivation, just follow the same steps, do everything that I've done over here, and we'll end up with the following. We end up with dH equals Cp dt, and then plus the specific volume minus T, and then times del V del Tp dP. And this equation I want to call 6a. And then I'm going to integrate just like I did before. So the integration on dH is just going to be the change in enthalpy, H2 minus H1. Then we're going to integrate on temperature, Cp dt. And then we're going to integrate on pressure. So V minus T, del V del T P dP. Okay. So again, we have some relationships in terms of what we want, right? Measurable as well as unmeasurable properties. And again, hopefully somebody in a research lab somewhere is using all this information and generating good property tables. So let me just pause and see if there's any questions on these relationships. Yes?
How did you get the pressure ratio? Like,
The pressure ratio?
the relative pressure on the top grid.
This one?
Yeah.
Oh, that's just our definition of specific heat. Specific heat at constant pressure is just defined as a partial of H with respect to T holding P constant, much in the same way that CV is just defined as the partial of U with respect to T holding V constant. So these are just definitions. Okay. So again, any questions? All right, so at least now we have a couple of relationships that involve internal energy and enthalpy. But let's also generate some relationships that relate entropy to some of these other properties. So we're going to do kind of the same thing one more time, actually 2 more times, 3 more times if I have enough time today. So let's start from S as a function of temperature and pressure. And again, we're going to write this in the form of equation A. So again, we're starting pretty much the same way. So we'll note that ds is equal to del S del T P dt, and then plus del S del P T dP. Okay. This equation, I'm going to call equation 7. So that's what we're going to start with now. And once again, I need to fiddle with other equations. I'm going to have to go back to another one of my TDS relationships, just like I've done before. So now I'm going to take the partial with respect to T holding P constant of the second TDS relationship, the equation that I call equation 2. Did I ever rewrite equation 2 anywhere? Yeah, it's that one, dH equals TDS plus PdV. Okay. So I'm going to do that, and I get del H del T P is going to equal, in fact, let me write equation 2 just so I have it handy. dH equals TDS plus PdV. All right, so I take the partial with respect to T holding P constant. So I have del H del Tp. And then here I have my second term. So T, and then this would be del S del Tp. Okay. And then the last term is just going to be 0. Well, why is that going to be 0? Well, we're taking the partial with respect to T holding P constant. If P is constant, then there's no delta P. Oh, did I do this right? Oh, I wrote down the wrong TDS relationship. In fact, I wrote it down wrong over there too. So no wonder it doesn't look right. This should say plus VDP. VDP. And see, these are things you're supposed to correct me on. And this is A plus VDP. Yeah. So just correct equation 2 as I've written it twice incorrectly now. Now hopefully it's correct. All right, so the statement was still correct. If we're going to take the partial holding P constant well, p is constant, right? So dp is just going to be 0. So we have that equation, but isn't del H del Tp by definition Cp? Okay, so let's just rewrite one more time. And basically we would get that Cp, and I'm just going to move the T over to the left-hand side. So Cp over T is just going to equal the partial of S with respect to T holding P constant. Okay. Now, unfortunately, I'm not really done yet. This is certainly important. But what I want to do is I'm going to take this equation, and then let's also note the fourth Maxwell relation again. And this was del S del Pt equals minus del V del Tp. Hopefully I have that right. Anyway, we're going to do like we did before, and we have these two equations that we plugged into, well, we plugged them into 5, we plugged two equations into 6. We're doing the same thing now. Here's our del S del Tp term, and here's our del S del Pt term. So we're just going to plug both of these into equation 7 to get the following. So let's see, we get ds equals, and then the del S del Tp term, well, that's just my Cp over T. So Cp over T dt. And then the second term is this one. In fact, we'll include the minus sign. So minus del V del Tp dp. Yeah, dp. Okay, so here's a useful equation. And once again, this is exactly the kind of equation that we're looking for. We're trying to find entropy in terms of other properties that we can measure, such things as volume, temperature, and pressure. Okay. Now, I do want to do the same thing that I finished these other equations. You know, I would like to integrate. So let's just do that integration. So the integral delta S, of course, is just S, evaluated from 1 to 2, S2 minus S1. And then we had the integral from T1 to T2 of Cp dt over T. And then minus the integral from P1 to P2 of del V del T, del V del Tp. Uh-oh. Okay, why is my equation not right again? Oh, it is right. dp. I was looking at the wrong equation in my notes. Okay, honestly, this is my least favorite lecture. Well, actually, the one on Friday is really my more least favorite lecture. But nonetheless, we'll get through this. All of us will together. So here's the equation that we're looking for, and I'm going to call this one equation 9. Now, I might note that there should be some elements of these previous equations that look similar, or I should say, look familiar to you. I mean, for instance, we think about ideal gases, and eventually I will specifically talk about ideal gases. All these equations are just general, but if we have an ideal gas and we're trying to find the enthalpy change or trying to find the internal energy change, isn't du just equal to Cv dt for an ideal gas? Yeah, I mean, that's something that we've talked about, at least in our last thermal class. Isn't dH just equal to the integral of Cp dt? Isn't the entropy change just equal to the integral of Cp dt over T plus some other term, which kind of looks similar to this one, but not entirely the same. It turns out that those relationships for ideal gases are actually derived from these equations. When ideal gases were first presented to you, I just used general words. We talked about how certain terms are just going to disappear because they're not strong functions. You know, for instance, H and U are strong functions of temperature, but weak functions of pressure and volume, and we're able to simply neglect certain terms. But I just presented you with equations back in ME301. Now we have the real relationships. And for an ideal gas, when we look at this next time, I'm going to actually show how these relationships, like 6A and 5A and 9, how these relationships actually are the same as the ones we've already talked about when we were talking specifically about ideal gases. For now, though, let's just continue talking about these general relationships. So let's do one more derivation here today. And again, I'm not going to go through all the steps, but I'll just say similarly. And this time, I'm going to look at entropy as a function of temperature and specific volume. So similarly, from S as a function of temperature and specific volume in the form of equation A, we would write the usual. So ds equals, and this is the partial of S with respect to t, holding v constant, dt, and then plus the partial of S with respect to v, holding t constant dv. Okay. So this equation I'm going to call equation 10. And once again, we're going to go through the same general steps as the previous derivation. In other words, this derivation that I just started right here. So again, let me just summarize for you. So once again, we're going to take one of the TDS relationships and turn it into a partial. So we're going to take d by d t holding v constant of equation 1, the first of the TDS relationships. We're also going to note, like we've done over here, that CV is defined as del U del T with V constant. So we'll note that CP is del H del T P. Okay. Is that what I want to do? I'm sorry, my notes are a little confused. No, I am. No, I use CP for that equation. This one I need CV. In fact, I said CV, but then I wrote CP. Sorry about that. Okay, so flying pen. Okay, so CV is del U del TV. This we know. Okay, so like I've done over here, I'm going to do some rewriting, if you will, and some mathematical manipulation. So rewrite, and then further note that we're going to take now the third Maxwell relation. And we're going to plug both. Now when I say both, we're taking dt dv of one equation. We're going to plug this definition of CV into it. We're going to rewrite the equation. Again, I'm skipping some steps, but we're going to end up with an equation somewhat similar to this one. We're then going to modify it. We're going to note the third Maxwell relation. And now we're going to plug them into equation 10. So plug both into equation 10. Okay. So this then becomes ds equals, now the del S del TV term is going to be very similar to what we had over here. It's just going to be CV dt over t. So this is CV over t dt. Okay. And then we're going to add to that. And again, we're going to have the Maxwell relation, the third Maxwell relation, which is going to take care of our del S del VT term. So you really just plug that in directly. And that's going to be del P del TV, and then dV. Okay. So this equation is going to be called equation 11. And then last but not least, I would like to integrate. So I get S2 minus S1 equals the integral of CV dt over t. So this is integrating on temperature from 1 to 2. And then plus the integral, and here we're integrating on volume of del P del TV dV. Good. And that I want to call equation 12. Okay. So this is another equation now for entropy. If we had data on pressure and temperature and volume, then we have these other relationships that we could utilize to find data for entropy. So again, I could go through another bounding analysis type of problem. I'm not going to actually give you another example right now. But at least this gives us some more relationships that, at least on some level, we understand are going to be quite useful to us. Okay. So let me just pause for a second. So again, are there any questions on these derivations? Now again, I skipped several steps there. I know I said that before, and anybody who wants to can certainly go through this. And by the way, all this information is in your textbook, so it's not like you have only this one opportunity to understand these derivations. Certainly you can look in the book and see the derivations. Let me also note, however, I'm not going to ask you to go through any of these derivations on an exam situation. On homework, sure, you've got some where you're going to have to go through some of this. But by and large, I'm not going to be testing you on the actual derivations. It's really going to be the bounding analysis that we would use these various equations for. So please just keep that in mind. And be thankful you're not at Caltech. Okay. Yes?
When we're going through the homework and we're doing problems that involve CV or CP, what would we use? What value from the textbook? Will we use the equation that they've got on the table, or just like an average? Or?
I mean, in general, I wouldn't even give you an equation like this because we just don't have good data for CP and CV. I mean, we have CP and CV data for certain gases, but only really for ideal gases. And I generally wouldn't be giving you a problem like that. We just don't have the information we need. So I guess you could say in many ways that a lot of this is just illustrative of the kinds of derivations and analysis that one would do in the research world. But no, we don't have good data in our tables to do a good bounding analysis when we have CP and CV available. If you had to, what is it, table A2 part C? It gives you CP as a function of temperature, and it's a polynomial equation, and it's on a molar basis, so it's really CP bar, so you're going to have to divide out the molar mass to get CP, and then you're going to have to relate CP and CV through the gas constant. CP minus CV equals a gas constant, and it just becomes a kind of a mess to do all that integration. So I'm not going to give you anything like that. Right. Well, what I would like to do is one more brief derivation. And in this particular derivation, I want to start with equation 8. Okay, so that one. All right, so let's just start with equation 8. So ds is Cp dt over t minus del v del Tp dP. Well, it should be the same as the one that's right over there, which it is. Okay, good. Now, what we want to do is we want to write another equation and compare them. So if I take, I'm sorry, can't read my notes anymore. Okay. So here what I would like to do is I want to start with a note that this particular equation is actually in the form of equation A, right? Okay. In other words, dz is going to equal m dx plus n dy. Now, we should recall from last time all these different equations. This was just one of them that was derived for you. But if we have an equation in this particular form, then we have other equations that allow us to relate these coefficients. Okay? So I can relate the coefficients using the other equation, or one of the other equations, that I called equation C. Okay? Equation C was the one that said the partial of m, well, the partial of m with respect to x holding y constant equals a partial of y with respect to x holding, no, that's not quite right, is it? Well, it's in your notes as equation C, but let me just identify it so we remember. Yeah, so del m del y x equals del n del x y. Okay, so again, I'll just write that out, that del m del y x equals del n del x y. So if we have an equation that is in the form of A, we can use those other equations like B and C and D to develop new relationships. And this is the equation C that would hold as long as I have an equation that's in the form of equation A. Well, it is, right? So all I have to do is just recognize that, let's see, Cp over T is m, minus del V del Tp is n. X, of course, is temperature. Y, of course, is pressure. And Z, of course, is going to be entropy. So I have it in the right form. So let's just substitute in the various relationships now. So we would have, uh-oh. My page went away. Is that it? Yep. Okay. So let's rewrite this now. So we have del. Now m is Cp over T. So del of Cp over T, del P. P is y, right? And then holding x constant, which is temperature T. And then on the right-hand side, we have our minus sign. Then we have del. And then n is that partial. So partial of the partial of V with respect to T holding P constant, del T. And y again is P. Okay. Now I might note that we can modify this pretty easily. First of all, we would recognize that del of Cp dt over del P, if T is constant, well, the T is constant, it just comes right out of the differential. So we just have 1 over T of del Cp del Pt. And then on the right-hand side, we would note that del V del T P, and then you further take a del T P. Well, this is now just the second partial derivative. So that's then equal to minus the second partial of V with respect to T holding P constant. And then we just rewrite it one last time. We have del Cp del P T equals, and then I'm just going to move the temperature to the right, so minus T, and then times the second partial of V with respect to T holding P constant. So this equation is equation 13. And this is a good equation to have, right? We might note that those previous 4 equations, the ones for U and H, and then the 2 for entropy, they not only had, well, U, S, and H as unknowns in the equations, but they also had Cp or Cv as unmeasurable or unknown quantities in those equations. Now I have a way to find one of those, right? Here I have a relationship specifically between the specific heat at constant pressure and measurable properties, pressure, volume, and temperature. So if I have the right data, I could solve this equation, equation 13, to get my value of Cp, and then I can plug it back into the other equations, like equation 8, or was it equation, well, it's all erased now. It's equation 7 or 6 or something like that. So again, we have a useful relationship. Now, there's actually one other relationship that I want to derive, but I don't think I'm going to have enough time. And looking at your faces, some of you are about to nod off, and I don't blame you. So why don't we just end it here today? First, are there any questions about anything? All right, so we're done for the day. We're certainly still right in the middle of this. There's more material, more derivations to make, more example problems to give you, and we'll finish this all up on Friday. So please don't forget to turn in the homework that's due today. Solutions will be posted right after class. And I do have some old work to see Mr. Richardson. Otherwise, see you all on Friday.